In order to simulate common source amplifier, first step is in your folder execute file new cell view, then give the name of the cell as common source and give as CS, then view will be schematic, then say OK. Then it opens a blank schematic editor. In this you need to draw the schematic of common source. Common source amplifier has 2 PMOS transistors and 1 NMOS transistor. Let us pick the transistor by executing create instance. Browse from GPDK 180 library, select NMOS and choose the properties of the NMOS transistor as width is 6 micrometer, and hide this, place it here. Similarly, we can choose PMOS transistor. With the dimensions 8.86, micrometer width and 180 nanometer length. Hide it and place the After placing all the components, select the pins. We need 5 pins here. VDD, then BSS, then I bias, then V in. All these 4 pins are in the input direction. Hide them, place in the appropriate positions. VDD, then VSS, then I bias, then input. Then we need one more pin, that is for V out, and it should be in the output direction. Hide and place it here. After taking all the components, make the connections using the option create wire narrow. After completing the wiring, check and save the design for any errors. If it is error free, then we can convert this schematic into a symbol by executing create cell view from cell view. Then it will open cell view from cell view form. Say OK here. Then arrange the pin positions as per the requirement. In the left side, I bias and V in should be there. VDD should be there at the top. And VSS should be there in the bottom position. Arrange as per your schematic. Then say OK. Now it is showing the symbol for common source amplifier. In order to customize the shape of the common source amplifier symbol, just delete the rectangles, both inner and outer rectangles, and customize the symbol as per your requirement. Customized symbol of common source amplifier looks like this. Save this, then close this window, then close the window of schematic also. Then now in order to test the common source schematic what you have drawn now, you have to create a test schematic. For that, execute file new cell view under your library. Then now name of the cell should be CS test, because I am trying to test the common source circuit. Say OK. It will open a blank window, schematic window. Here we need to draw the test schematic by picking the appropriate components. First step is execute, create instance, then browse for the components. The first component is common source symbol. It will be under your library. Pick it, then place it in the window. Then the remaining components are DC voltage, then DC current source and AC voltage source and a capacitors. These are supposed to be picked from the respective libraries and it should be connected. For creating test circuit, after picking up the common source amplifier symbol, remaining components are to be picked from the respective libraries. For example, for this VDD, you need to pick VDC from analog lab and the value of this should be 3.3 volts. And for capacitor, it should be cap, the cell name is cap and it is from analog library and the value is 500 femtofarad. And for this input voltage, you need to apply two sources. That is the first one is V sign with the AC magnitude as 1 volt and AC amplitude as 10 micro volts. Then frequency should be 10 kilohertz and the DC voltage is to be separately applied and the value of that should be 592 millivolts. And the bias current for the transistor should be taken as IDC and the value should be 303 microamperes. After this, connect the circuit using the option create wire. Then after completing the connection, the circuit looks like this. Then check and save the design for any errors. If the circuit is error free, then we can start with the simulation. In order to verify the functionality of this circuit, we need to launch the simulator, that is ADEL. By executing ADEL, it opens analog design environment simulation tool. Then first step is you need to choose the analysis. For choosing the analysis, choose execute analysis choose. It opens up choosing analysis window. There, in order to do the transient analysis, click on tran, then select the stop time. In order to observe 10 cycles, each cycle clock's given frequency is 10 kilohertz, means the clock is the period is 0.1 millisecond. In order to observe 10 cycles, you can give the stop time as 1 millisecond. Then set the accuracy details as moderate. Say OK. Then the transient analysis arguments will appear in this field. Then what are the outputs to be plotted? I am going to execute outputs to be plotted. Select on design. I need to observe the input. Then I need to observe the output. Then after selecting the input and output, execute the simulation by clicking simulation netlist and run. It will run the simulation and it will display the waveforms, input and output waveforms. These are the input and output waveforms for the common source amplifier. As we can observe from the waveforms, this is the input and this is the output. Output is 180 degree out of phase with the input as expected, because the common source amplifier is analogically equivalent to common emitter amplifier. Hence, there will be a phase shift of 180 degree between input and output. Next is we have to perform the AC analysis to find the gain. To perform AC analysis, go to analysis, choose, then click on AC. Then the sweep variable is frequency. Frequency has to be swept from 1 Hz to 10 gigahertz, for example. Then sweep type, let me choose logarithmic sweep. Then points per decade is 10. Say OK. Now we have to run the simulation by executing simulation netlist and run. It will plot the AC response, shows the frequency response of the common source amplifier, that is the gain versus frequency. As can be seen here, the maximum mid-band gain is 29.74 volts. This is the output versus frequency, that is, as we have chosen input as 1, V out by V in is same as V out. It is showing V out by V in, which is nothing but the gain to be 29.74 for 1 volt input. To measure the gain and unity gain bandwidth in ADE window, we need to execute results direct plot AC magnitude and phase. In order to execute this, before this we should have done AC analysis. Then if I click on this, then it will take us to the schematic editor window. There we need to choose V out. Then press escape. We can see the plot of magnitude versus, this is the magnitude and phase plot of the common source amplifier. As can be seen here, the magnitude, that is magnitude of the gain in decibel is 29.46 dB, and this is the phase plot, which is varying from 180 degree from here to 91 degree on the other end. And in order to plot the understand the UGB, it is nothing but the unity gain bandwidth. It is the bandwidth at unity gain. In order to calculate the unity gain bandwidth, place a cursor or marker by executing create marker, and that marker should be in the horizontal direction. Say OK and move this marker to 0 dB. That is, whenever I select 0 dB, it is the unity gain point. Then here, wherever this unity gain point intersects with this frequency response plot, that is the actual unity gain bandwidth. That founds to be around, suppose if I keep the marker here, cursor here, it is showing it is 1.25 gigahertz. That is the UGB for the common source amplifier what we have designed now. To do the DC analysis of the common source amplifier, execute analysis, choose, click on DC, then turn on save DC operating point, then sweep variable should be chosen as component parameter. It will take the, if I click on select component, it will take me to the schematic editor. There you need to choose the DC voltage source and select the component parameter as VDC, then say OK. Then in the choosing analysis form, you need to specify the value, from what value to what value we are going to sweep. That is from -5 volts to +5 volts. Then say OK. Then in ADE, execute the simulation by clicking on netlist and run. This is the DC analysis plot of the common source amplifier. It is resembling that of an inverter because of the 180 degree phase reversal between the input and output. That means whenever the input is low, output is maximum, and whenever the input is high, output is minimum. That is, it's almost like a inverter VTC we are going to get. The designed common source amplifier, the gain will be 29.4 dB and UGB will be around 1.25 gigahertz. To draw the layout of common source amplifier, execute launch layout Excel from the schematic window. Then it will ask, as I've already drawn the layout, it is showing can I open the existing. If you are drawing it for the first time, it will you may have to click create new, say OK. Then it's going to open the blank layout editor if it is drawn for the first time. As it is already drawn, it is showing here existing layout. In order to draw this, you have to execute like connectivity, generate all from source. If I click, it's going to generate all the devices, that is 3 transistors and 5 pins. Automatically layout will be generated. Then you need to connect the remaining wiring as shown here as per the schematic. This is the PMOS transistor. This one is second PMOS transistor to which we have applied I bias, and this is the NMOS transistor for which we are applying the input voltage. Then after completing the connections as per the schematic, the final layout looks like this. Then in order to check whether any errors are there, DRC errors are there, you have to execute the DRC check for this. For doing that, first you need to select the technology file by executing Ashura technology. If I click, then you have to browse for the path and you need to select this path, that is home. Under home you have install folder, then under install you have foundry, then under foundry analog, and under that 180 nanometer, under that Ashura underscore tech.lib library file has to be selected. Then say OK. Then for executing the design rule check, perform Ashura run DRC. If I click on this, it will ask open a run Ashura DRC form. Here initially it will be in undefined. Then you need to set this as GPDK 180 technology file. Then after setting the technology to GPDK 180, say OK. Then it will run the DRC check and it's going to show the results. It is showing there are no DRC errors. If there are any DRC errors, you need to debug the errors. Then only you need to proceed further. That is, if the design is clear from the DRC errors, next step can be executed. Once the DRC errors are cleared, then execute the layout versus schematic check by performing Ashura run LVS. Then here technology file I need to set as GPDK 180. Then say OK. After matches between layout and schematic, it has to be debugged. Now it is in progress. After performing the LVS check, it will show if at all if there are any errors. Once LVS is completed, it's going to show the results in this form. And as you can see here, 0 cells have 0 mismatches. That means all the cells and nets and pins are perfectly matching with the schematic. Then say yes. It's going to show the result in a separate window. Here we can see schematic and layout match. Only after seeing this comment we can proceed further, because this indicates layout and schematic are perfectly matching. Once it is done, next step is RC extraction. For performing the RC extraction, execute Ashura run Quantus QRC. Then in this parasitic extraction run form, first you need to select the extraction type. Observe output will be in extracted view and view will be AV extracted. Then go to the second tab, extraction. Here you need to select RC because we are trying to extract both R and C. Then set the reference node as VSS. Say OK. Then it will run the RC extraction and the result will be available in a AV extracted view under your library. Once the RC extraction is completed, it's going to show the result in this window. Then it is showing it is completed successfully and it is available under your library with the name AV extracted view. Close and go to your library. You can see there is a AV extracted view here. Click on this and open AV extracted view. This is the RC extraction of the common source amplifier, and if we zoom it, we can see R and C values which are extracted. These are the parasitic capacitors and parasitic resistors which are extracted. Once the RC extraction is done, then we need to proceed for the post layout simulation or back annotation. For executing back annotation, click on the circuit which that is the test circuit which has to be tested, then execute file new cell view. Then in new cell view form, change the type to configuration config. Automatically this view will be config and open with will be hierarchy editor. Say OK. Then it's going to open new configuration window. Under this top cell, select view as schematic using drop down option. Then click on use template and select the simulator as spectral. Then say OK. Then all these library list will be filled here. Then say OK. Then in this hierarchy editor window, there will be two views, table view and tree view of the design. Click on tree view. Then here if you click on I0, you can see all the parasitics which are being extracted. Right click on I0 and set instance view as AV extracted, because we are trying to simulate the post layout values. Therefore set the common source view as AV extracted view, which will have RC information. Then after setting this RC values, then save the design by clicking on save icon, then say open. Now the test schematic will be open. If you want to see what is this common source amplifier view, just right click on this, then click on descend edit. In a new tab, we can observe that common source amplifier symbol is nothing but it is replaced with the AV extracted view. Then go back here and try to launch the simulator to see the post layout values by executing launch ADEL. Once we launch it, if the session is already saved, then just click on session load state, then say OK. Then here transient AC and DC analysis are to be performed. First I'll click on AC analysis, then simulation, netlist and run. If I do, we are going to get the results in a waveform window. As can be seen here, the gain is 28.92, which is lesser than the pre-layout value, which was 29.5 volts. Now it is reduced because of the inclusion of RC into the circuit. Transient analysis can be performed by executing simulation, netlist and run after clicking transient analysis. Then these waveforms indicates the output and input. As seen here, output is 180 degree out of phase with the input, which is similar to your pre-layout waveforms except the magnitude changes. Then finally DC analysis has to be performed. In order to perform DC analysis, enable DC here under ADE window and execute the simulation by clicking on simulation, netlist and run. This is the result of DC analysis. As can be seen here, the DC response or the voltage transfer characteristics resembles that of an inverter because of the 180 degree phase reversal between input and output. This completes the complete simulation of common source amplifier, right from the schematic capture till the back annotation.